So for this video, we're going to pick up where the flipped class video left off for the velocity and tangent lines. So let's just start by recalling what we saw in that video. So let's recall. So in that video, we defined the average velocity. Over an interval, say a to b, as well, we can write this as v, say, sub average, so AVE to stand for average. This is S of b minus S of a over b minus a if, say, y equals S of t is the position function. So that means our velocity average is going to have units. Well, it's the units of s divided by the units of b. So this will be something like meters per second, feet per second, meters per hour, something where it's a distance divided by a time unit. So what we can use this for is we can use this to approximate the velocity. At some time t0, so we use this by choosing an a and a b so that t is in that interval. So we could write this as t is in the interval ab, which is the same thing as saying a is less than or equal to t is less than or equal to b. Let's say t0 here. We're using t0 for our spot. And if this a and b are close together, this will be a better approximation. So the closer a is to b, the better the approximation. So let's go ahead and look at another example of this. Okay, so let's say the position of a ball thrown in the air. So let's say this is S of t is, let's say, 10 times t minus 4.9 t squared. And here we're going to have S of t is measured in meters. And t is measured in seconds. So we want to estimate the speed, which we might also refer to as velocity, of the ball after 2 seconds. So that's our goal. We throw the ball up in the air. We have this position function given by S of t. We want to estimate the speed of the ball after 2 seconds. So that means, we want, from our above setup, we want t0 to be equal to 2. So that means we want to consider a and b with a less than or equal to 2, less than or equal to b. So there's a few ways you'll see this done. Is we could say, so for one example, we could take a to actually be 2 and b to be bigger than 2. We could take a to be less than 2 and b to be equal to 2. Or we could just take on both sides, so a less than 2 less than b. So any of those ways works for an approximation. So let's go ahead and make some charts to get this estimate. So we'll make some tables. So let's start with the first one. So for the first one, let's go ahead and take a to be 2 and b to be bigger than 2. So for this chart, we might take some values of b that are close to 2 but bigger than 2. So maybe we look at like 2.1, 2.01, 2.001, 2.0001. So we're getting closer down to 2. And then let's go ahead and find those average velocities. So let's look at S of b minus S of a over b minus a, which for us is S of b minus S of 2 over b minus 2. So we can just plug these values into our function above. So for instance, our we're just going to take this function here, S of t equals 10t minus 4.9 t squared, and we'll plug these values for b in and for 2 and look at this difference. And if we do this, we get that this is minus 10.09, and then this is minus 9.649, minus 9.6049, and minus 9.6005. So just to make sure we understand what's happening here, when I look at this S of b minus S of 2 over b minus 2, I'm plugging in this 2.1. So this is S of 2.1 minus S of 2 over 2.1 minus 2. And then we actually plug those values in. So for the first term, I'll have 10 times 2.1 minus 4.9, 2.1 squared, minus 10 times 2 minus 4.9, 2 squared, all over 2.1 minus 2. And if you work all that out, this is minus 10.09. That's where those numbers in the table are coming from. I just went ahead and evaluated them and stuck them in there for us. So for this, we can see our estimate from this value is this is our approximate speed. Okay, so the closer b gets to 2, the better the approximation is. So using a equals 2 and looking at that, that's our approximation. So now let's set a to be less than 2 and b to be equal to 2, and let's do a table for those values. So same idea, take our a here, and we'll look at S of 2 minus S of a over 2 minus a. And so the values of a being a little bit smaller, maybe we look at like 1.9, 1.99, 1.999, 1.9999. And if we evaluate these, they get minus 9.11, minus 9.551, minus 9.5951, and minus 9.5995. So for this one, if we did this value, we would estimate this as our estimate for the speed at t equals 2. So if we look at these two values together, we might guess, well, the first one's a little bit off of 9.6, and the second one's a little bit off of 9.6. So we might actually guess the speed at t equals 2 is minus 9.6 meters per second. And that negative sign, what does that mean? Well, that means the ball is coming back down. So the one other way we could do this is we could use a is less than 2 is less than b. So let's go ahead and make a chart for or a table for this. I'm going to have values of a, values of b, and then S of b minus S of a over b minus a. So if we do this, we can take the same type of thing, 1.9, 1.99, 1.999, and then say 2.1, 2.01, 2.001. And if we fill these in, we actually turn out to get minus 9.6 every single time. So that tells us then our estimate's pretty good. So we'll take our estimate for the speed at t equals 2 seconds to be minus 9.6 meters per second. So we can also think about, what does this mean graphically? So let's think about graphing our equation for s of t. So we start here at 0, we're going to go up, and then we'll come back down somewhere like this. So let's say y equals s of t. And then we have 1 is somewhere here, 2 is somewhere like this. So if we look at, say, when we look at, say, s of 2 minus s of, say, 1.9 over 2 minus 1.9, we should view this as this looks like a change in y over a change in x. So if I go here to this point 2, this is height s of 2, and then if I go to 1.9, we exaggerate it a little bit to make it right here. And so if I take the line that connects these two, like this, so this is the line through the points 1.9, s of 1.9, and 2, s of 2. And so then that average velocity, which is s of 2 minus s of 1.9 over 2 minus 1.9, we see that's exactly the slope of this line. So we often call, when we have a curve like this, and we have a line that goes through 2 points of the curve, we refer to this as a secant line. So what we see then is our average velocity is actually giving me the slope of a secant line. So if we think then, well, what's happening is we take these points, we're letting the values get closer and closer to 2. Well, if you think about what's going on here with the graph, let's think about zooming in, say. Let's pretend we zoomed way in on our graph. So we're much closer now. So say just looks like this. And we'll exaggerate a little bit to make it look a little bit better for what we're trying to do. So let's say this is y is equal to s of t. And so if I look at a couple of points here, let's say this down here is at 2. So this could be, say, the secant line. Say if we've zoomed way in to exaggerate, this would be 1.9. And then we can move a little closer, say, let's try to get a different color if I can. Let's try this one. And so let's say if we use a little bit closer now, say this is 1.99, we're not necessarily going to scale here just to give us a little better picture. Now we have this secant line here. We pick another color. Say now we're way over here. Now we take the line through these two. We can see what's happening as we get closer and closer here is we're coming closer and closer to a line that just touches the curve at that particular point, which is what we refer to as a tangent line. So if, let's just draw this one more time, zoomed in, and just look at, say, a particular value for this. So if I have my curve here again, it looks like this. Say, and let's say right here, say this is the value for 2. Well, if I take a secant line that's very close, say this is 1.99, and I look at that secant line, you can see as that gets closer and closer, it becomes a better and better approximation for the tangent line, which we'll draw here, say in pink, which is just this line. So this line just touches the graph at one point. So that tells me those secant lines are getting closer and closer to our tangent lines. In this case, as A gets closer to 2, the secant lines get closer to the tangent line. But we also know those secant lines, the slopes of the secant lines are our average velocities. So as A gets close to 2, the average velocity gets close to the instantaneous velocity. So if we put all that together, we see the slope of the secant, or the tangent line, is the instantaneous velocity. Tangent line at, say, t equals 2 is the instantaneous velocity. At t equals 2. So what we're going to want to do is we're going to want to figure out a way to make precise what it means for A to get close to 2, and how to calculate this without having to make a big table. To make a table and kind of guess, like above we just saw, well, it looks like it's getting close to this number, so we'll guess that's true. We don't really want to have to guess. So this will lead us to the notion of limits. Which are useful for not just for these calculating the instantaneous velocities. We'll see lots of ways that they come up, but it will answer this problem for us. But before we move on to limits, let's try one more example to make sure we really understand what's going on with these slopes of these lines and how to compare them. So we have the position of a particle is given by the following graph. Let's go ahead and make our graph. It's supposed to be a t. Set y here, and let's tick off some. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4 going up. Now let's make a graph. Here, so we'll start here at 1. We're going to go up about until we hit 4, and then we'll turn around like this. Okay, so that's what our picture looks like. So what do we want to answer about this picture? So let's arrange the following from smallest to largest. So the first thing, let's say the average velocity between t equals 1 and t equals 3. The second one, let's say the average velocity between t equals 5 and t equals 6. Let's say the instantaneous, I'm going to abbreviate that, velocity at t equals 1, instantaneous velocity at t equals 3, instantaneous velocity at t equals 5, and for the last one, the instantaneous velocity at t equals 6. Okay, so let's look back at our picture for a second. So we notice here, from about this point here on, the lines will all have negative slopes. So for instance, if I look at say the tangent line here, which would give me the instantaneous velocity, that has a negative slope. And if I look here at 5, this one also has a negative slope, but it's less negative. And then the one connecting these two is somewhere in between. So that tells me this one, and this one, this is negative, negative, and negative. And then we just saw from above that the tangent line at 6 is the most negative. So I'd have f as the very smallest one. It's the most negative. And then after that, it looks like the average velocity between 5 and 6 is then, so this line right here, going here, that connects those 2 points, that looks like the next one with the steepest negative slope. So that would be B. And then the one after that would be the slope of the tangent line at t equals 5. So that would be this one. And then we know those are all less than 0. So now let's start looking at some of these other ones. Let's get a different color for this. So if I look at the instantaneous at t equals 1, that would be the slope of this line here. So that's positive and somewhat steep. If we look at here at 3, if we get a different color for this one, say, looks something like this. So it's a little bit flatter. So I know that the instantaneous velocity at t equals 1 is bigger than the one at t equals 3. And then I can look at the instantaneous velocity, or the average velocity between 1 and 3. And again, that's going to be something like this. So it's somewhat between these two. So the biggest one will be the slope of the biggest slope will be the red line, and then the orange, and then the green. So if we go down here and fix this, so the next one should be the instantaneous velocity at t equals 3, because that was the somewhat flat green line. And then after that, it was the average velocity, so then that will be A, and the last one will be C. So you think of the steeper, if I have a line where it's increasing, the steeper this is. So if this is like this one has larger slope. And then it's the opposite if they're negative. So make sure you spend some time making sure you understand how we got those, because it's good to have a good feeling for kind of reading off the graph what a large slope and what a small slope looks like.